Now in 1.5, we're going to look at inverse functions and logarithmic functions. So first of all, what is an inverse function? Essentially what inverse functions do is they flip the input and the output around. And here's a formal definition. Suppose that you have a one-to-one function f. So what one-to-one means is that for every x value, there's a unique value of y. So if that is the case, then it has an inverse function, and it's denoted by f and then a superscript of -1. It looks like a power of -1, but it is not. And so what that means is if you have y is equal to f of x, that's equivalent to, this means equivalent to, by the way, right? So this equation is equivalent to saying that f inverse of y is x. So you can see hopefully what's going on. In this case, x is the input, y is the output. But in this case, y is the input, x is the output. In other words, they have flipped around. And an easy way to visualize this is by looking at these diagrams. So this blob A is your domain of the function f, so meaning the x values. So what goes in here are 1, 3, and 8. And this blob B is the range of f, meaning what comes out, the y values. And the function f will take you from here to here, and so on. Notice that no two y values are repeated. Each x value gets a unique value of y. Then what f inverse does is it goes backwards. So instead of going from 1 to 5, it takes 5 and outputs 1. So everything has reversed. What that means is that the domain of f is the range of f inverse, and the range of f is the domain of f inverse. Now there are some properties of the function and its inverse in that they have the effect of canceling each other out. Not actually canceling, but the effect of canceling each other out. So that happens when you compose the function with its inverse. Here's a composition of f with its inverse, and here's another one but reversed. So f inverse is composed with f. It turns out no matter what the order is, if you compose a function with its inverse, then what comes out is what you started with in the beginning. So in this case, x. So that's what I mean by they have the effect of canceling each other out. We're not actually canceling them out, but they have the effect of that. And again, I wanted to emphasize that this does not mean f to the -1. This means inverse. So these two are not equal. So what if you did want to write f to the -1? How you would write it is like this. So this does mean f to the -1. That means these two things are equal. All right, now let's look at the inverse function of the exponential function y is equal to b to the x. Now for it to have an inverse, remember it needs to be 1 to 1, meaning for every x value, you need to have a unique y value. Is that the case for exponential functions? Well, let's go back to our graph of exponential functions. And if you remember, if your graph of a function passes the horizontal line test, then it is 1 to 1. So what is a horizontal line test? It says that if you draw a horizontal line at any point, your graph should cross that horizontal line at most once. So let's see if that's true for a randomly chosen exponential function. Let's, for example, choose this blue one here, y is equal to 2 to the x, ignore everything else. Draw a horizontal line anywhere you want. Notice that this horizontal line crosses the blue curve exactly once. And it'll turn out that no matter where you draw this horizontal line, the graph will cross that horizontal line at most once. So it is 1 to 1, and that's not unique to just this function. It's true of all of these other functions as well. So now that we know that it's 1 to 1, let's try to find its inverse. Now, in general, to find the inverse means to solve for x, solve for the input variable. But using the elementary operations like adding, subtracting, multiplying, dividing, and powering, you can't isolate for x. So what happened here was that mathematicians decided to come up with a new function that represents the inverse of this exponential function. And that function is called the logarithmic function. So let's define it formally. A logarithmic function is a function of the form y is equal to log base b of x. And how you read it is log base b of x. What it is called is a logarithmic function with base b. And if this is the case, if y is log base b of x, then this is equivalent to saying that b to the y is x. So if b to the y is x, then it's the same as saying y is log base b of x. So we've actually solved for y here in this equation, meaning we found the inverse of this exponential function. It's log base b of x. Now notice that now I've gone back to y as b to the x instead of x is b to the y. Again, because x and y are just variables, you can switch them around in this case. So I've gone back to our usual way of writing the exponential function, y is b to the x. And y is equal to b to the x and y is equal to log base b of x are inverses of each other. If you remember from high school, you learned how to draw the graph of the inverse given the graph of the original function. We already know what the graph of the original function is. It's the exponential function, so it's like this, assuming that b is bigger than 1. Now, this function, what will it look like? Well, because we know that it's the inverse of the exponential function, what we can do is reflect the graph of the exponential function around the line y is equal to x. So that's this dotted line here. So imagining that this is the mirror, draw what you see in the mirror, and it'll be something like this. So that's your graph of the inverse. That's the graph of log base b of x. All right, and if you remember those two properties of the function and its inverse, remember if you compose them in whatever order you want, they have the effect of canceling each other out. Let's write that using f of x is b to the x and f inverse of x is log base b of x. So if you want to write this for these functions, what you have to do is into the function f here, you're going to plug in f inverse of x, which is this. So this becomes the input of your function f. So it'll look like everywhere you see x here, you're going to plug in f inverse of x, which is log base b of x. So you get b to the power of log base b of x. And that's equal to x according to that equation. And this is something that's worth remembering. Just think of b and the log base b kind of have the effect of canceling each other out. It's not exactly canceling out, but it just has the effect of canceling out. Now similarly, the other way to compose is f inverse of f. So how we can write this is we go to the f inverse, and wherever we see x, we plug in f of x, which is b to the x. So we're going to get log base b of b to the x, and according to this equation, it's equal to x. So again, the log base b and the b kind of have the effect of canceling out, although it's not exactly canceling out. And let's look at some special cases of this one here. Again, you should memorize this one. When x is 1, let's see what we get. We get log base b of b is 1. You should remember that as well. And finally, when x is 0, what we get is, well, b to the 0 is 1, so we get log base b of 1 is 0. You should also remember that. Alright, so some properties of logarithmic functions. All the graphs of log base b of x where b is bigger than 1 look like this. They're all increasing functions. And note that they all go through the point 1, 0. And that's because your exponential function always went through 0, 1. Every point on the graph of the exponential function gets flipped around, meaning x becomes y and y becomes x in the inverse graph. And so since your exponential function goes through 1, 0, flip the x and the y coordinate around and you get 0, 1. That's where the inverse function goes through. And another way to think about it is by looking at the equation itself. The reason why the graph of log base b of x goes through 1, 0 is that if you plug in 1 here, log base b of 1 is 0, if you remember from the previous page. And so that's another reason why your graph goes through 1, 0. Right, because log base b of 1 is 0. The domain, remember, is all the input values that you can have so that the output is a real number. So there are two ways to figure this out. You can either look at these graphs and conclude that you can only have the x values starting from bigger than 0, because there's nothing on this side or on the y-axis, going all the way up to infinity. Right? These do go on forever. So the domain is from 0 to infinity. Another way to think about the domain of the inverse function is by looking at the range of the original function. Remember, the domain becomes the range and the range becomes the domain. So if you remember, for the exponential functions, the range was 0 to infinity. And that's why the domain of our logarithmic function is 0 to infinity. Now similarly, the range is all the y values or all the output values that the graph takes on. So looking at these graphs, you can see that, well, this goes down forever, this goes up forever, so the range is all real numbers. Or again, you could have just looked at the original function, y is equal to b to the x, and look at its domain. Remember that the domain was all real numbers. That means the range of the inverse is all real numbers as well. Now, as I discussed earlier, there is a vertical asymptote at the y-axis, and the equation of the y-axis is x is equal to 0. What a vertical asymptote is a vertical line that the graph gets closer and closer to. And we'll talk more about vertical asymptotes in terms of calculus later in the course. Now let's look at some properties of logarithms. Now there's a product in here, x times y, inside the logarithm. It turns out that we can turn that into an addition. So what I mean is you can write it as log base b of x plus the log base b of y. So the logarithm has the effect of turning a product into a sum. Now similarly, notice that there is a quotient in here. Logarithm has the effect of turning a quotient into a subtraction. So what that means is we can write this as log base b of x minus log base b of y. And finally, there's a power here, power of r on the x. What the logarithm does is it brings the power down, so it turns the power into a multiplication. and it looks like this: r times log base b of x. All right, so knowing these three laws of logarithms, we can try this one. It says to evaluate this number, and the final answer will just be an integer. Again, please pause this video here and try to work on it yourself first. So notice that we have two different logarithms that are subtracted. It kind of looks like this. So what we will do is turn this into a single logarithm by going backwards, right? So we'll write it as a quotient. So this is the same as log base 2 of 80 over 5. Well, 80 over 5 is 16, so this is log base 2 of 16. Now it is simpler, but it's not as simple as it can be. I want to get rid of this log base 2 altogether because I want the answer to be just an integer. Well, if you remember, there is a property like this. So if you have a log base b out here and inside there is a exponential function with base b, then they have the effect of canceling out. So we want to use that property in our example. Now we have a base 2 in the logarithm, and inside, well, it's not an exponential function, but we can write it as 16 to the 1. But we can't really cancel these out because this number is not the same as this. So we will first have to make those the same. And the easiest way to do that would be to turn 16 into a power of 2. Well, 16 is 2 to the 4. And now notice that these two are the same. So using the property from before, they have the effect of canceling out. And we're left with just 4. So there's your answer. Now, just like how we looked at the exponential function e to the x separately, we're going to do the same thing for logarithms. So logarithm base e is called the natural logarithm, and it even gets a special name. So instead of this here, we usually write it as ln x. And we read it as just ln x. Now remember these equivalent equations. Let's try to rewrite these with b equal to e. So then this becomes ln x is equal to y. And an equivalent way of writing that equation is to say e to the y is x. In other words, the inverse of e to the x is ln x. So nothing new here, we just have a new notation for log base e. And remembering those two properties from before, we can also substitute e for b for those two things. And this one's going to become e to the ln x is equal to x, which you should memorize. And similarly, this other property, when you plug in e wherever you see b, is going to become this. Ln of e to the x is x. You should also memorize that. And in particular, if you plug in 1 for x here, you're going to get ln e is 1, which you should also memorize. Now you can pause the video here to work on these two examples. The first one is asking you to solve for x, and x is in the power. So whenever you're trying to solve for a variable that's in the power, using a logarithm will help you out. And this is what I mean. Well, first of all, you're going to have to get rid of any number that's multiplied by that exponential function. So we're going to divide both sides by 2. So that's going to give us e to the 5 minus 3x is 5. And now that you just have an exponential function out here, what you can do is take the natural log of both sides. In other words, log base e on both sides. And you'll see why in a moment. So when I do that, I get ln of e to the 5 minus 3x is equal to ln 5. And hopefully it's obvious now why I did that. The ln and the e have the effect of canceling out. So the left side simply becomes the power. 5 minus 3x is equal to ln 5. Now we all know how to solve for x, so let's do that. I'll bring the 3x onto the other side, and I get 5 minus ln 5 on the left. Divide both sides by 3. So x is 5 minus ln 5 over 3. Now for the second equation, the x is inside the logarithm. So you need to get this out of the logarithmic function. And how you do that is by raising both sides to a base e. So again, because there is a number in the front multiplied, you have to get rid of that first. So we'll divide both sides by 3. So that gives you ln 2x plus 1 is 6 over 3, which is 2. And then raise both sides by a base e. And you'll see why in a moment. So when we do that, e to the ln, remember, have the effect of canceling out. So all we're left with is 2x plus 1 on the left side and e squared on the right side. Now again, it's easy to solve for x. 2x is e squared minus 1. That means x is e squared minus 1 over 2.